In this lesson, we will discuss 5 topics. The first one is the Voronoi diagram. The second one is the Delaunay triangulation. And after that, we will look at the duality between these two data structures. That is, these two, the Voronoi diagram and the Delaunay triangulation, represent the same thing, simply from a different point of view. Then we will look at how we can construct the Delaunay triangulation, and also because these two structures are dual, it also means that we can construct the Voronoi diagram. And finally, we will look at 2 special cases of the Delaunay triangulation, that is the constrained Delaunay triangulation and also the conforming Delaunay triangulation. Let's start the lesson with the Voronoi diagram. If we speak of a Voronoi diagram, we speak of a set of points. So let's say we have some elevation points that were collected around. We start by projecting these points to the 2D plane, as we saw in previous lesson. So if we have a set of points on the plane, for example, the around 25 points that we have here, then the Voronoi diagram creates, well, if we explain it simply, proximity cells. So it means that every point that we can call a generator creates one cell, as you can see here. So if we have 25 points, let's say now, then we have 25 cells, and each cell represents the space that is closer to the points generating the cell, so the point in the middle, let's say, than to any other points. So if we are here, if you look at the point P, for example, here, we can say that all the points, so all the XY locations that are within the cell that is around the point P, are closer to P than to any other points. Let's see how we can create the Voronoi diagram for a few points. So if we start with one point only, let's say we have one generator, then there's only one Voronoi cell, and that Voronoi cell is unbounded. So its area is infinite, so it covers the whole plane. Then if we add a second point, for example, that one, so we have now 2 generators. How it works? Well, it's pretty simple. We can just look at the line segment that connects the 2 points, and then we find the perpendicular bisector. So if we look in the middle of the line segment and we look at 90 degrees, then we can simply draw the line segment that we call the perpendicular bisector. And then if we remove the line segment, and we obtain 2 cells. So we have one cell that covers one cell that represents the space that is closer to the point on the left, and the one on the right is also a Voronoi cell. Now let's add a third point, a third generator. So let's say we add a point here. Then the same procedure can be followed. We find the bisector, we draw the line segment that connect every pair of points. In that case, we have 2 because we already have 1. And then we draw the perpendicular bisector of all line segments. So here it would be around something like this. Continue like this, and then here it would be something like this, I assume. Then we can remove the line segment that connects the 2 points, and we can also remove the parts that are not interesting for us. This one. And then we obtain something like this. So it means that now we have, well, they go at infinity. We have 3 Voronoi cells that are all unbounded. And what you should notice if we look at some characteristics, so we know that if we walk along the line here in red, we also know that if we're here, then we're at the same distance from that point and that point. Notice also that if we stand here, the junction of the 3 Voronoi cells, we know that we are exactly at the same distance from 3 points, that point, and that point. And if we continue to walk along that line, so if we know that if we're here, then we're at the same distance from that generator and that generator. Since drawing by hand is not my forte, as you might have noticed, you can now see how it looks like if we have a interactive app where we just click and then we can insert one point after the other. A few things to notice about the Voronoi diagram. you notice that when we started, the cells were unbounded, but if you can see here, many of the cells are bounded. To know which one are bounded and unbounded, it's pretty well. If you can notice here, you can see that the blue ones, for example, that one, and that one are bounded. But this one, and for example, that one are unbounded. So you can see that because that one, if you just continue the lines, they will never converge. But for example, that one would be bounded because if you just continue the line, so the Voronoi cell will go beyond the arbitrary rectangle that we have put as a spatial extent, but this cell is bounded. So the cells that are unbounded are this one, that one, that one, that one, that one, and that one. So if you just join them, you obtain what we call the convex hull. The convex hull is the smallest convex polygon that contains all the points. So if we look at the 12 points in that set here, we can conceptualize these points as nails that are sticking out of a table, for example. So if you want to know what's the convex hull, we simply take an elastic, and then if we let go the elastic, then the polygon that we obtain, well, the boundary of the elastic is basically the boundary of the polygon that defines the convex hull. One last remark about the Voronoi diagram is that so far we've seen how it looks like in 2 dimensions, but it's also possible to have the Voronoi diagram in 3 or 4 dimensions. So in 3 dimensions, we simply replace the 2 by a 3, so we have the Euclidean space in 3D. So if we have a set of points in 3D, then the Voronoi diagram has exactly the same definition. It also creates proximity space, just that these proximity cells, just that these cells are now not convex polygon, but convex polyhedra. Here you can see 2 points and their respective Voronoi cells if there were other generators around. And the gray plane that you see separating these two is not the perpendicular, is also the perpendicular bisector, but instead of being only one line here, it's basically a plane that separates these 2 points in 3-dimensional space. Given a set of points in the plane, instead of subdividing the plane into Voronoi cells, it's also possible to subdivide that plane into triangles, for example. Well, actually, we will not subdivide the whole plane into triangles, but the convex hull of the set of points. So in the case of the set of points here, so what we can do is that we can subdivide its convex hull into triangles. So one solution we can obtain is that one here. So we have a set of triangles, but as you can notice, some of the triangles, so for example, that one here or that one here, are very long and very skinny. This is a property that's not desirable in terrain modeling. This is something that we will discuss in a future lesson. So what we do usually in terrain modeling is that instead of using any triangulation, we use what is called the Delaunay triangulation. So this is here a Delaunay triangulation. The one that I just showed wasn't a Delaunay triangulation. So a Delaunay triangulation has the unique property of having its triangle with an empty circumcircle. So it means that if we draw the circle around each triangle, this circle will be empty of any other points. I'm not very good at drawing circle, but as you can see here, if we draw the circle around every triangle, then this circle should be empty of any other point, any other generator. So if we go back to the previous one, you can easily see here that if I draw, for example, the circumcircle of the triangle here, which would be this triangle here, then it will contain several points. And that's the same for many others. If you do it here, for example, if you notice here, this one is very tiny. So if we try to draw the circle, it will be a massive circle that will contain several of the other points, for example, that one and that one. The Delaunay triangulation has a very interesting property, and this property is called the max-min property. And that says basically that the minimum interior angle of every triangle will be maximized. So this means that long and skinny triangles will be avoided. The max-min property and the empty circumcircle of the Delaunay triangulation can be clearly explained if we simply build the Delaunay triangulation for these 4 generators. So then we would start by defining the convex hull. And then after that we have 2 choices. Either we do the diagonal like this or like this. If we start with the one like this, and you can clearly see that if I draw the circumcircle, then this point here is inside. And if I draw the circumcircle of that one, then this point is inside. Also, you can notice that here the angle are pretty small. In comparison, if we choose the other diagonal, the only other possibility that we have, then the empty the circumcircle is empty, the angles are better and are bigger, and also the other one is empty. It should also be said that the Delaunay triangulation is unique. So given a set of points, we know that there's only one Delaunay triangulation. But this is only if the points are in what is called the general position. So that means that there shouldn't be any co-circular point. If we have co-circular points, so let's say that we have a given circle, and then if we put 4 generators on this circle, 1, 2, 3, 4, then when it's time to decide which of the 2 diagonal we should use, this one or that one, then you can notice that both are valid, because for both there's no points that are inside. So it means that here we have an ambiguity. We can decide which Delaunay triangulation is valid, and actually both are valid. So if you have a big data set where you have several points, but then suddenly there's many points that are co-circular, then you can see, you can assume that there's not an infinity, but that there's several Delaunay triangulation that are valid, because inside the circle here, any diagonal would be valid, and then there's more than one, there's more than only one solution. There exists a duality between the Voronoi diagram and the Delaunay triangulation. The duality implies that these 2 structures represent the same thing, just from a different point of view. And this duality also implies that every element of the planar graph of the Voronoi diagram, so Voronoi diagram is formed of vertices, edges, and the embedding in the plane implies that we have faces. So every element of the Voronoi diagram has a direct correspondence to every element of the Delaunay triangulation, also if we look at it from a planar graph point of view. And this correspondence is easily explained. So we know that if we have a vertex in one graph, it's mapped to a face in the other one. We know that if we have an edge, it's mapped to an edge. And we know that if we have a face, it's mapped to a vertex. So if we start with the Delaunay triangulation, the Delaunay triangulation that we can see here, and if we start with this one, so if we say that we have faces and we try to map them, we map them to every face becomes a vertex. So if every face is a triangle, so we know that, for example, here I can say this triangle is mapped to a vertex, this one as well, this one as well, this one as well, and this one as well. And actually I just put the points in the more or less in the middle of every triangle, but I know from the definition of the Voronoi diagram and the Delaunay triangulation that the location of a point is actually defined as the center of the circumcircle of a triangle. So if I draw this, then I know where they can be located. Notice that here my triangles are more or less equilateral, so there's no so the point is located more or less in the middle. But if I looked at another triangle, for example that one here at the bottom, if I draw the circumcircle, it's pretty big, and it's very much possible that the dual Voronoi vertex of this triangle here, it's possible in that case that it's located outside, but this is completely okay and this is not a problem. So now that we've done the faces to vertex, then we can look at the other part, which is mapping every edge of the Delaunay triangulation to an edge of the Voronoi diagram. So if we look at the edge here, we know so it will be we know that it's going to be mapped to another edge, and then the other edge will simply be linking the two center of the triangles that are incident to that one. That should be at 90 degrees. It's not exactly, but you get the idea. And then if we do that for all of them, then we obtain the Voronoi cell for the generator that we have here. And then we can continue to do it for other points. So for example, I could join that one here, this one here, and then I would obtain the Voronoi cell for the point here. And then if I continue, then I joined in the same manner if I did the mapping for all the edges, then I would obtain the Voronoi diagram for the same set of generators. So it's possible to go from the Delaunay triangulation to the Voronoi diagram this way, but it's also possible to go from the Voronoi diagram to the Delaunay triangulation by applying the same idea. As we've just seen, the Delaunay triangulation can always be extracted from the Voronoi diagram and vice versa. So it means that if we want to construct either structure, we can just construct one or the other and then extract the other one on the fly. As we can see here, we are actually, when we're clicking, we're just constructing the Voronoi diagram, but in practice, probably, I don't know what's behind that code, that's a web application that I found. The Delaunay triangulation is probably the structure that is being constructed and maintained, and simply the Voronoi diagram is displayed. Actually, there are algorithms to construct directly the Voronoi diagram, but these are more complex to maintain and to implement. And usually in practice, people will implement the Delaunay triangulation and then extract the Voronoi diagram on the fly. Let's discuss one algorithm to reconstruct the Delaunay triangulation. It's called an incremental algorithm. An incremental algorithm means that we construct a Delaunay triangulation by starting with already a Delaunay triangulation. It can be a very simple one with 3 points, and then we incrementally, let's say we have 10 more points, we simply update the Delaunay triangulation with a 4th point. So we insert it, we update the Delaunay triangulation, so we have a valid Delaunay triangulation, and then we insert a new one, the 5th one, we update it, and we continue. This is possible because of a property of the Delaunay triangulation, that is, given a Delaunay triangulation, it can always be updated, and it can be updated locally. This is shown here. So let's say we have a Delaunay triangulation on the left, and we have 12 points, and then we would like to insert the point here in red, the point in the middle. If we want to insert that point, we can see here that the insertion of that point will only affect a certain number of triangles in a Delaunay triangulation. And these triangles are shown in gray here. So it means that if we want to insert that point, the point here in the middle has not been inserted yet. The insertion of that point will only invalidate a certain number of triangles, and there's only 4. And these 4 triangles are the one in the red area here. This is based on the property of the Delaunay triangulation that says that the circumcircle of every triangle needs to be empty. So basically what we show here is that the insertion of the point here will render on Delaunay 4 of the triangles in that Delaunay triangulation. So here we had only maybe around 15 points, but in theory, if we had several other triangulations, if we had a triangulation of 1 million around, then the insertion of this point would also create only, would also delete only 4 triangles. So triangle 1, 2, 3, 4 here would be deleted. And then what the Delaunay triangulation does is that it retriangulates this polygon. So here the gray area that by the insertion of the point creates a polygon, and it needs to be retriangulated, and the retriangulation creates here, as you can see on the right, 6 triangles that are all incident to the point P that was just inserted. Let's see how that would work for 3 points. So for example, if we start with these 3 points here, we can easily create the Delaunay triangulation, which is the only triangulation possible. So the incremental algorithm starts by inserting new points. So as long as we insert points inside the triangulation, so what we do is that if we want, for example, to insert a point here, what we do is that we find the triangle in the Delaunay triangulation that contains this point. In this case, there was only one, so that was this. And then we split this new triangle into 3 new triangles. And if we continue this, so for example, here we find a triangle, we split that one into 3. We can also do that in the triangle here. So you can see that if we continue this algorithm, then we always maintain a triangulation. The problem is that we create very long and skinny triangles. So for example, the edge here would be pretty long, and if you remember, if we look at the circumcircle, we can see that if we draw the circumcircle around this one, then it would contain another point. So the idea of the algorithm is that we insert points, but to ensure that the Delaunay criterion is respected, after each insertion, the triangulation is updated, but there's a next step that's necessary, and this next step involves what is called flipping. So for example, we identify here that the edge is not Delaunay. So what we can do is that we can delete that edge, and the idea of flipping is simply to replace it by the other edge. So we had 4 points here, this point, this point, this point, and this point. There were 2 ways to triangulate it. We had 1 way, so now what we did is that we modified it. So the idea of the Delaunay triangulation is basically to do that. So if we do it for another point, if we inserted the point here, for example, then we would split this triangle into 3 points. But so we can see here that the circumcircle around that triangle would contain other points. So the idea here would be to simply again delete, for example, that edge and then insert another edge that is more Delaunay. You can see here the steps that are required for the insertion of a single point and different flipping operations. So flipping is basically flipping the diagonal of a polygon that has 4 points. So there can be 2 diagonals, so we can flip the diagonal. So basically the insertion algorithm states that you insert the point and then you start a series of flips that will update the triangulation so that all the circumcircles are empty. As a last topic for this session, we're going to speak about 2 variations on the Delaunay triangulation, the constrained Delaunay triangulation and the conforming Delaunay triangulation. These 2 triangulations are necessary if the input that we have to our Delaunay triangulation is not only a set of points like we had so far, but a set of points and line segments. These line segments, we would like them to be recovered in the final triangulation. By that I mean, for example, if we take the set of points and the set of line segments and we simply triangulate them with the way that we've seen so far, what we obtain is a triangulation that will not recover the edges. So we have here the 3 edges, but as you see, these edges are not part of the Delaunay triangulation. And this is not something that we wish to have if, for example, we have in a GIS application, we have a set of elevation points and we also have a set of polygons. So for example, we have the buildings of a given area. We would like to obtain a triangulation where the buildings are embedded into the triangulation. So where the buildings are not going over the set of triangles that we obtain from the triangulation. So if we want to do this, then we need to use the constraint and or the conforming Delaunay triangulation. Given a set of points and line segments as input, the one in the middle is the constraint Delaunay triangulation and the one on the right is the conforming Delaunay triangulation. Both are called Delaunay triangulations, but they have completely different properties. The first thing to notice is that the conforming triangulation is a real Delaunay triangulation in the sense that the circumcircle around every triangle is empty of any other points. While the constraint triangulation, if you draw the circumcircle around every triangle, so this one is empty, But this one, for example, wouldn't be empty because the point here would be located inside that triangle there. So this one, the constraint is not the constraint Delaunay is not a real Delaunay triangulation. The conforming Delaunay triangulation, it should be observed that it's a real Delaunay triangulation, but only because new points were added. So these new points are called Steiner point. And in this case, we have added 2 points, and these points allow us to have a new triangulation that has more points. But the advantage of this is that every triangle is a real Delaunay triangle, which has an empty circumcircle. In the case of the constraint Delaunay triangulation, the empty circumcircle rule has been eased. That is, every triangle is empty of any other points, but there's a visibility constraint, and this visibility constraint is such that the line segments are blockers or visibility blockers. So it means that if we draw the circumcircle of the point of the triangle here, for example, this triangle here, we notice that the point here is inside the circumcircle, but it doesn't matter because this point here is not visible from the other triangle. So this point here will not see that point because the original line segment acts as a visibility blocker. But it also means that the number of points in the input and the number of line segments are the same, so which is a big advantage, but the property that we maximize the minimum angle of every triangle is not respected. While if we use a conforming Delaunay triangulation, then if we allow more points to be inserted, which also means, for example, that our original line segments might be split into 2, 3, 4 or more parts. So if we allow this, the advantage is that our conforming Delaunay triangulation is a real Delaunay triangulation.